Hello, I am Aleks Vartanian,
And this is Slatin.
and we are doing our project on a heated sink. So unlike the problems we've done in labs, our problem is a transient temperature problem as opposed to a structural problem. And we're trying to see if we could find how long it takes to burn yourself if you leave your hand on the edge of a metal sink while hot water. So the basic parameters we're using for this analysis, through that we're going to analyze the effect of we're holding a constant temperature at the bottom of the sink, which is 212 degrees, which is equivalent to boiling water. So the bottom of that sink that you can see highlighted in red is going to be held at 212 degrees Fahrenheit the entire time. And then we're just going to see how that held temperature is going to affect the rest of the sink over time. So through that, we're going to use 3 different element sizes. We have a coarse, medium, and fine element size. And again, through those element sizes, we're going to see if the changing the element size has an effect on the time it takes for the edge to reach a certain temperature.
So we took into account many assumptions when doing this model. The temperature of the base of the sink was held constant at 212 degrees to represent boiling water in the sink. The temperature of the metal that is touched is the temperature of the skin, so that's when we burn your skin, that's basically the same temperature as the metal. And this is going to occur at the very top of the sink where it takes the longest for the energy and the heat to transfer. We're ignoring convection and radiation in this problem. We're strictly focusing on conduction. And all the energy of the hot water is going directly into the sink in this assumption. So conduction, to review for your heat transfer, the equations displayed here equal to negative times the conductivity times the surface area times the temperature gradient, and we have the equations for convection and radiation as well, but those are ignored.
Okay, so through this analysis, we looked at a few different levels of burn for your hand on the sink. So we looked at 1st degree, 2nd degree, 3rd degree, and like complete destruction of your skin cells. So each of those are shown. So we're looking from beginning at 120 degrees to 162 degrees. So we're going to see how long it takes for the metal to reach all those temperatures. Alright, and so now we have a visual representation of our model. So if you look on the left, here's a GIF of the temperature change throughout time. And as you can see, it starts heating from the bottom, and then the part we're looking at is the upper left-hand corner, which is currently yellow. And that's where it just shows what we want to see at the very end, how long it takes for that part where your hand's going to be to get a certain temperature. And on the right, you see there's a graph that shows the temperature distribution of that part over time. So it's not linear, and it's changes over time. And then this also shows the effect of the material. So one of the things you want to see is how changing the type of material affected the temperature over time. And so as you can see, different materials such as copper have a much higher thermal conductivity as opposed to stainless steel, which has a very low thermal conductivity.
So this is our graph of basically all of our findings. It's organized in types of burn, so at the very bottom is the 1st degree burn, and the top is the time for total skin destruction. And these big long blue bars are stainless steel, and you can see it's going to take the longest amount of time to burn yourself with a stainless steel sink because of the low conductivity of stainless steel. Whereas if you look at the small green bars, that's copper. So if you make your sink out of copper, not a very bright idea. Heat will transfer through it very quick, exponentially quicker than if you use stainless steel.
And then another effect we wanted to look at was the effect of mesh size on the temperature distribution. So we couldn't find a definite relation between the mesh size and how long it took to reach a certain temperature. But what we did find is that depending on how long you took to record the time, there's a different standard deviation between the different mesh sizes. So if you just looked at the 1st degree burn, the soonest recording that we found, there was a very small deviation between the different mesh size times. But as we went up and up and up in time, as we went up to destructive time, which was 162 degrees Fahrenheit, so that was like the longest time, the distribution between the different times for each mesh was much larger. So that pattern just sort of shows that the longer the analysis went on, the more distributed and varied the times were between each mesh size.
So to conclude, a common sink that's made out of stainless steel, it's going to take about 20 minutes to get a 1st degree burn by touching the top of the sink. But if you're an unintelligent person and make your sink out of copper, you're going to burn yourself in 30 seconds by touching the same spot. Don't make your sink out of copper.